Hey everyone, and welcome back to WirelessPro. We're back with the third installment in our AI in 3 GPP series. In our previous video, we explored how AI is making beam management in 5G and beyond incredibly smart for faster, more reliable connections. Well, today, we're shifting gears to another critical area where AI and machine learning are making a massive impact: positioning accuracy. Imagine your phone knowing its location with pinpoint precision, down to mere centimeters. That's the ambition for 5G Advanced and 6G. We'll uncover the limitations of current positioning methods and then dive into how 3GPP is leveraging AI to overcome these challenges, enabling hyper-accurate location services for a whole new world of applications. Let's get started. So how does your phone know where it is right now, especially on a 5G network? Traditionally, it's a bit like a high-tech game of hot or cold. We call these geometry-based methods. Imagine your phone, or UE, listening for signals from multiple base stations, or G-node BS. One classic technique is time difference of arrival, or TDOA. Think of it like this. Each G-node B blasts out a special signal. In 5G, we often use position reference signals, PRS, allocated in different bandwidth parts, BWPs, for organization. We also use sounding reference signals, SRS, for the uplink case. Your phone measures the tiny differences in arrival times of these signals. By comparing these differences, we can draw imaginary lines or hyperbolas, and where they intersect, bam! That's your phone's estimated location. It's super clever, and we call this multilateration or hyperbolic positioning. Now, while these geometry-based methods are great, they do have one issue. Their kryptonite is line of sight, or LOS, conditions. What does that mean? They work best when there's a clear, unobstructed path between your phone and those G-node Bs. But what happens in a dense indoor factory or a bustling city with towering buildings? Signals bounce off everything. We call this a dense multipath environment, and it can seriously mess with those delicate time measurements. Think of it like trying to hear someone clearly in a noisy, echo-filled room. The accuracy just degrades. And with 5G Advanced and 6G targeting mind-blowing centimeter-level accuracy, traditional methods just aren't cutting it. That's where our heroes, AI and machine learning, step in. 3GPP, the global standards body, has been hard at work figuring out how AI and ML can supercharge positioning. They've identified two main approaches. First up, we have direct AI-ML positioning. This is where an AI model directly determines the UE's location. Imagine taking a fingerprint of the radio environment at different spots, like the unique pattern of signals or how they travel. This can involve analyzing things like channel impulse response or power delay profile as input. Then, the AI learns these fingerprints, and when it sees a new one, it knows exactly where your phone is. Then there's AI-ML-assisted positioning. Here, the AI acts as a super smart helper. Instead of giving the direct location, it generates intermediate measurement statistics that are then fed into traditional positioning algorithms. This could be anything from figuring out the probability of a clear LOS to accurately estimating the angle a signal arrives from, or even refining time of arrival measurements. It's all about making those existing methods even better. Let's get a bit more specific. Imagine an indoor factory setting, like the one you see here, with 18 TRPs, transmit/receive points, laid out in a grid. For this challenging environment, we're putting a powerful AI brain to work, a ResNet Convolutional Neural Network, or CNN. You might have heard of CNNs from image recognition. They're great at finding patterns. ResNet is a super advanced type of CNN, known for its ability to handle very deep networks. Why is this important for positioning? Because in scenarios like indoor positioning, where fingerprinting is key, these models can learn incredibly complex relationships between the radio signals and the physical location. They're trained on vast amounts of data, often generated from 3GPP channel models, to become master location predictors. So where does all this AI magic happen? Who's doing the heavy lifting, the training, and the inference? The beauty is, it can be distributed. The AI model can reside on your UE, aka your phone, in the Location Management Function, or LMF, a network entity responsible for location services, or even at the G node B, the base station, itself. 3GPP has categorized this into three main ways the positioning can play out. First, direct AI/ML positioning. In this scenario, the AI model is directly applied to the raw measurements to determine the location. This can happen on the UE, the LMF, or even the G node B, depending on where the AI model is deployed and executed. Next, we have assisted AI/ML positioning with multi-TRP. Here, the AI is used to enhance measurements or generate new measurements, and these AI-assisted measurements are then used for positioning. The multi-TRP signifies that measurements from multiple transmission and reception points, TRPs, are leveraged, which could involve the UE providing assisted measurements to the LMF, or the G node B generating them for the LMF. And finally, assisted AI/ML positioning with single TRP. Similar to the multi-TRP assisted approach, AI is used to assist measurements, but in this case, the assistance is derived from a single TRP. This could involve the UE generating AI-assisted measurements based on a single TRP, or the G node B providing AI-assisted measurements from its own perspective to the LMF. It's a really flexible and powerful framework designed to get us to that elusive centimeter-level accuracy, no matter how challenging the environment. Alright, let's see AI/ML positioning in action. This is our WirelessPro platform, specifically our Visual Studio Code environment. Right here, you can see a snippet of the ResNet CNN model code we discussed, the very core of our AI brain. Our project files, clearly visible here, cover everything from training data generation to ML model training and inferencing. Now for the results. These two graphs powerfully illustrate the UE position estimation error. On the left, for direct AI/ML positioning, notice how the AI/ML-based curve is significantly better, showing much lower error rates than traditional methods. And on the right, AI/ML-assisted positioning also delivers a clear accuracy boost. WirelessPro demonstrates that AI and machine learning aren't just standards. They provide superior positioning accuracy essential for 5G Advanced and 6G. And that's a sneak peek into the incredible world of AI and machine learning for positioning accuracy in 5G Advanced and beyond, as defined by 3GPP. This is just the beginning of hyper-accurate location services that will power everything from smart factories to augmented reality. If you found this video helpful, make sure to install and try out WirelessPro. We'd love to hear your thoughts. So let me know in the comments what other 5G Advanced and AI topics you want us to explore. Thanks for watching, and I'll see you in the next one.